All right, so this is the fluids chapter. Very basic information here about the fluids. Week 13 is going to be the continuation of that with adhesion and cohesion as well. So first off, properties of fluids. So fluids, right, are substances that can change shape and fit the container that they're in, right? There are two different types of fluids though, liquids and gases. So there's a big difference between gases and liquids in their compressibility. So compressibility is whether or not you can compress a gas, squeeze it down, change its volume like that. So liquids are practically incompressible while gases are compressible. So the volume of a gas can be increased, decreased, you can press on it, right? You can expand it. Using a piston, for example, that's usually the go-to example for that. But liquids are highly incompressible. So even if you apply a very large force, it'll not change the volume by much, right? This is just a very quick overview of density. Density is mass over volume. I think that's a pretty common concept that you guys have probably gone over in a lot of your other classes. What isn't so common maybe is specific gravity, and specific gravity is the ratio between the density of your substance that is in question that you're looking at, and then, so the ratio for that substance density to the density of water, right? So if I, for example, took, let's say, I don't know, 1,060 kilograms per meter cubed for blood. If I want the specific gravity for blood, I just take 1,060 divided by 1,000 kilograms per meter cubed to get my specific gravity for blood. And then that will give me basically kind of a ratio or a factor that I can multiply by the density of water in order to get the density of the substance. So if I were told that the specific gravity of blood is 0.6, for example, let's just say it was that. If it was 0.6, I know the specific gravity. I know specific gravity is the density of the substance divided by the density of water. So I can just take the specific gravity multiplied by the density of water, and then that gives me the density of the substance, right? So it's just multiplying the specific gravity by the density of water to get the density of the substance. So if they were to give you the specific gravity, you can find out the density of the substance in question just by multiplying the density of water, right? And this is a really quick conversion factor as well that's important. More likely than not, it's going to be given to you. It's 1 liter is equal to 0.001 meter cubed, right? This is a quick example, just conversion once again with this stuff. So if you have, they're asking you the density of water in grams per milliliter. If you've taken any of your science courses, you'll probably know that the density of water is 1 gram per milliliter. If you don't know that, right, or if they ask you to convert or something like that, you do know though that the density of water in kilograms per meter cubed is 1,000 kilograms per meter cubed, right? This is really important to know once you get to the hydrostatic pressure equation and once you get to Bernoulli's equation. So you can take 1,000 kilograms per meter cubed, you can convert from kilograms to grams, right? So you divide, or you multiply by 1,000, kilograms will go with kilograms, grams will be left on top, and then if you want to convert from meters cubed, you know that 1 meter, 1 meter is 100 centimeters, and then you cube that. Don't forget to take the exponent to the third there in order to have the proper units. So meters cubed has to cancel with meters cubed up here, and the only way you can do that is if you cube the whole factor. So 1 meter is 100 centimeters, right? But you can't just divide by 100. You would have to take this, raise it to the third power, and then divide, right? And then 1 centimeter cubed, this is an important conversion factor as well, is 1 milliliter, right? So if they were to ask you as well, if they said, what's the density of mercury, right? If you have the density of mercury, right, as what, 13,600 kilograms per meter cubed, that's the density of the substance. We can look at that, divide by 1,000, that gives us our specific gravity, right? So specific gravity is 13.6 in that case. That's our ratio. Now, we know that the density of water is 1 gram per milliliter, right? So this ratio tells us when we get 13.6, it means that the density of mercury is 13.6 times the density of water. So if we know the density of water is 1 gram per milliliter, then 13.6 times that density gives us 13.6 grams per milliliter as the density of mercury. Make sense so far? You guys can see it, right? I just want to make sure because like my head is big, I know. All right, so this is pressure, right? So now we're getting into the pressure stuff. So pressure is defined as the ratio of the force to the area, and that's applied throughout a surface, right? The units for pressure are Pascals or newtons per meter squared. Pressure is not constant. As you go down, pressure increases, and there's derivation for that I can explain here later on. But generally, as you go deeper, right, as you go down, sink deeper, you increase in pressure. As you go upwards, you decrease in pressure. this is a very quick kind of example here as well with the manipulation of this equation. Pressure is equal to force over area. If they were to tell you that the atmospheric pressure, which this is also another important factor here, 1 atmosphere is 10 to the 5th pascals. That's your pressure, right, in pascals for your pressure equation here. If they told you that you have a column filled with water, the top of this column has an area of 10 centimeters squared, that's your area right there. What is the force exerted by the atmosphere on top of this column of water? And what force does the water exert back on the air, right? So first of all, you have this pressure, 10 to the 5th pascals, right? You got to make sure everything is in SI units. So if we have pascals, we know that it's in newtons, meters squared. That indicates everything has to be in kilograms, everything has to be in meters squared, right? Those values are in SI units. So if we have 10 centimeters squared, we can't just plug that into the area simply, right? So what we would have to do is convert that first to meters squared, right? So we know 10 centimeters squared, we know that 1 meter is 100 centimeters, right? Like I said before, with that problem that we cubed, we take it squared now so that the centimeters squared will cancel out, right? So that'll leave you with meters squared on top here, right? Meters squared. So I think that gives you 0.001 meters squared for that answer. So all you'd have to do is multiply the area by the pressure. So 10 to the 5th pascals times 0.001 meters squared, and then that should give you a force of 100 newtons, right? So that's the force exerted by the atmosphere on water, right? There would have to be an equal but opposite force from the water column on the atmosphere as well to cancel that out. So 100 newtons as well, water on atmosphere. Now, there's also viscosity. We're not going to get into viscosity with this specific set of slides. The next week's concepts, which is week 13, that'll be factoring viscosity, Reynolds number, stuff like that a little bit more. But just so you know, kind of have an idea from the beginning, viscosity is just kind of measure of the stickiness, thickness of fluid, right? And so that's measured in Pascal seconds or newtons times seconds per meter squared. You really don't have to know this part so much. Just make sure that you know that it's Pascal seconds. But these are just some different values for viscosity. We don't really have to know that at the moment. Now, velocity for a fluid, that can change, and we'll go into this here in a second. That'll change depending on changes in area, for example, and that'll be factoring in with the continuity equation. And like I said, we're going to go over that in a second. So not every single point in a fluid will have the exact same speed. It might change depending on if you have a change in area or not. This also is part of the week 13 stuff, bulk modulus, so I'll leave that later. But this brings us to pressure. So we already said that pressure is everywhere in a fluid, right? Force divided by area, that's what pressure is defined as. There's not much that you really have to kind of know else for this slide. The only thing is that this might be, I could see this being kind of maybe an exam problem, possibly. Just the idea that they might not always give you a simple pressure problem like, here's a column of water, what's the pressure at this height, what's the pressure at that height. What they might do instead is all right, here's, these are the type of problems that I can see them kind of doing. If they were to give you I don't know, a beaker of water, right, or a piston in this case, and it's compressed, right? So this piston is being compressed, this spring is being compressed due to the pressure of the atmosphere. So it might be compressed a certain distance, right? Now with this spring, what kind of force do we have going on? Spring force, right? So with this spring force, like I said with that earlier example, whatever force that the atmosphere acts on the column of water, the spring in this case, there must be an equal and opposite force, right? So that equal and opposite force would be that spring force. Because if I'm pushing down like this, if I'm causing a displacement downwards like this, the spring force is actually in the opposite direction because it's a restoring force. It helps restore your initial equilibrium, right? So if I'm going back like this, that's that equal and opposite force because I know the atmosphere is pushing down on the piston. So if they were to ask you or give you a situation like this, the way you would figure things out, the way you'd figure out the pressure or the force from the atmosphere is looking at the displacement, how much this spring is displaced by. They might give you a spring constant. You figure out the force. Once you figure out the force, you know that pressure is equal to force over area. And so that the force that you use is the spring force divided by the area of that piston right there, right? To get your pressure, because you know the force from the spring is going to be equal and opposite to the force from the atmosphere. Does that make sense, that kind of scenario there? Any questions at all? Okay. That's the only thing I think that's probably maybe unique about this slide. Otherwise, I think that's it. This here is kind of a derivation of the hydrostatic pressure equation. I can go over it really quickly here. So whenever you have like a column of water like this, you have a force acting downwards at the top of the column here, force acting upwards from the bottom of the column, and then you also have gravity, right? So with these forces, they can each be kind of, I guess, rearranged or written in terms of pressure as well. So we know that pressure is equal to force over area, right? So we know that the force A downwards like this is equal to the pressure of A times A, because we know that pressure is equal to force of A divided by A. So if we multiply by the area, we should see that the pressure at A times the area is equal to the force at A. Same thing for B, right? If we have pressure of B is equal to the force of B over A, we can just multiply by the area, and we can see that the pressure of B, I think this is an error. Pressure of, oh, my bad, not this. I was looking at something else. Pressure at B multiplied by the area gives you the force at B, right? And then finally, you have your gravity. So gravity we know is mg, right? If you remember from like the buoyancy chapter, which I know we probably all hate, I hate it myself, but this mass can be rewritten as density times volume, because density is equal to mass divided by volume. So if you just multiply by volume, the volumes cancel out and you're just left with mass. So another way of rewriting mg for force of gravity is density times volume times gravity, right? Now, what is volume though? If we look at just, remember like kindergarten math, middle school math, volume is area times height or base times height or whatever, right? And so in this case, you can rewrite the volume as well as area times height. So you have now three components, three forces, right, that are acting on this column of water. You have a force acting at the top of the column, force acting from the bottom of the column, and the force of gravity. If we were to write a net force for all these different forces, right, they'd also all have to cancel out, because the column of water, if you're just looking at it, it's not moving, there's no net force, right? So if we were to look at it and write a net force equation, we can see that FB pointed upwards minus mg minus FA pointing downwards, both of them, should equal 0. And so if we rearrange the equation, we can see force of B is equal to mg plus force of A, right? If we were to grab these forces and then plug in the pressure times area equivalent of them, right, from the rearrangement of the pressure force equation that we had from earlier, we can see that the pressure at B times A, the area, is equal to the density times the volume times the gravity. That's our force of gravity there, right? And then the force of A added to that as well, which is the pressure at A times the area. Then, if we rewrite the volume once again as area times height, what do you notice that's common in all of these terms in the equation? What's a common term? Well, oh, my bad. This is the only one that's density. These both are pressure. But what do you see that's common in each term? What does each term have as a variable next to it? I heard area, right? A. So A, and A. If you divide by A for the entire equation, you end up getting pressure at B is equal to density times your height times your gravity plus pressure at A times the, well, not area, my bad. Yeah, plus the pressure at A. So if you see then, that's pretty much the hydrostatic pressure equation. That's a derivation for it, because then we can see that it's the pressure at A plus the density plus gravity times the height at A is equal to the pressure at B plus the density times the gravity times the height at B, right? So that's the derivation for the hydrostatic pressure equation. Once again, this equation is just going to be available on the equation sheet, so you don't have to worry about memorizing it. I just figured to explain where this stuff comes from, because I think it's better if you understand like what's going on. But I don't think it's necessary to like understand fully the derivation, because I don't think they're going to ask you to like derive the equation or anything like that. But generally, before I go on to any of these hydrostatic pressure problems, the way I like to solve them or go about solving them is first I work from the bottom and then I go to the top, right? So I start from B, pressure at B. B I think of as bottom, right? So I start from the bottom and I go upwards. That way, whatever heights I'm plugging in will be positive heights, right? So I go here, height. Now, if you think about height, there's a connotation with height being positive. So if I say I'm at a height of 30 meters, you would think, oh, I'm 30 meters up in the air, right? But if I say I'm at a depth of 30 meters, what does that imply? I'm downwards 30 meters, right? So maybe I'm 30 meters below sea level or something like that. That's what it implies. So if you are able to set up your problem in a way that you start from the bottom and you go to the top, your height will be positive, right? If you were to start from the top and go to the bottom, which I've seen some students do, that's perfectly fine. Just know that if you're starting at the top and that's your reference height, that's your 0 meter height, anything downwards is going to be a negative height. So you have to plug in like a negative 30 meters or a negative 10 meters as your height in that case at point B for it to all work out properly. Otherwise, just start from the bottom. Now we're here. So that brings us to some different unique examples here and problems that we can solve. So first of all, based on the hydrostatic pressure equation, I'll write it up here. PA plus rho GHA equals PB plus rho GHB, right? With this equation, I already kind of have the answer up here anyway, but it's fine. Would this situation be possible? If not, why? Yeah, so the atmospheric pressure, right, because they're in contact with the atmosphere at the top of those columns right there. Atmospheric pressure is 10 to the 5th pascals, right? We're assuming obviously that this is one type of fluid, it's just water throughout. And so based on that hydrostatic pressure equation, well, if it's water is water, right? If water is water, then the density here and the density there are the same. Gravity here and the gravity here are the same, right? And the pressure at the top of those two different columns there should be the same because they're both atmospheric pressure. Well, if this is the same, 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 then shouldn't the heights be the same as well? That's the only logical explanation, right? Because if the pressures are the same at both columns, right, at both heights there, because they're in contact with the atmosphere, then assuming also that we have the same fluid, it's just water throughout with 1,000 kilograms per meter cubed density, and assuming also that gravity is constant, we should have the same height. So that's why this would be possible, because at this same height, you experience the same pressure, right? And that's another important concept too, that whenever you have two fluids that are the same, and you're looking at a specific height, so if I looked at these two heights here, I just drew a horizontal line like this, any two heights in the same fluid will have the same pressure. This is another example here. So it says an iceberg floats in a shallow sea. What can you say about the pressures at point 1 and point 2? So for point 1 and point 2, like I said, if they're at the same height, if you can just draw a horizontal line between them like that, if they're at the same height, they're at the same pressure. Why? If we go back to the hydrostatic pressure equation, we can see, okay, well, I'm trying to figure out the pressure here, pressure there. Well, if the density is the same, if they're both water, if the gravity is the same, if the heights are the same, right, they're at the same height or the same depth in this case, then let's say if this rho GHA term and this rho GHB term are both 30, for example, if you subtract over 30, 30 minus 30, that's 0. And so you're left with PA is equal to PB, right? So that's how you can kind of look at it from the hydrostatic pressure equation as well. But just know that generally, same fluid, same height, same pressure. Now this is an example with the hydrostatic pressure equation, using that with specific numbers to figure out different pressures, right? So it says water with a density of 1,000 kilograms per meter cubed, shown in the figure. What is the pressure at the top of the closed tube, assuming the surrounding air is at normal atmospheric pressure, right? So remember what I said about how to set up these types of problems. It's better to start from the bottom and then go to the top, right? So usually when I say bottom and top like that, right, I use the bottom, for example, as it could be, honestly, it could be my known value for pressure or it could be my unknown. In this case, the bottom pressure is the closed tube right here, and that's what's unknown, and that's what I'm trying to figure out. What is known is at the top here, right? Anytime you have a fluid just with air on top of it right there in contact with the atmosphere, know at that point it's atmospheric pressure, right? So here's PB, here's PA at the top, right? So with that, I can set up my hydrostatic pressure equation, and I can say pressure at A plus rho GHA equals pressure at B plus rho GHB, right? Pressure at A at the top here is atmospheric pressure because it's in contact with the air, right? So that's my 10 to the 5th pascals right there. For pressure at B, right, that's my starting position. If I'm starting from the bottom, whatever my reference height is, whatever my bottom height is, it should have a height of 0 because I'm starting there, right? So in that case, whenever your PB, or you're using that as the bottom, that's your reference height, then this HB term is 0, and so this whole term just goes to 0, right? There's no point in plugging in the values there. It's a waste of time. So you just have PB then is equal to the pressure at A plus rho GHA. So you just plug in your density value, your gravity, and your height at A. In this case, they gave us the height here. From here to here is 100. From here to there, it's 40. So if we subtract 100 minus 40, we should get this little distance here. That is 60, right? So we plug in 60 meters there for our height. So another thing that you can see here from this equation is that PB is equal to the atmospheric pressure plus another term. So that tells you automatically that it makes sense there for this equation, and it proves kind of the real life concept that you see, that as you go deeper, right, as you go down in the atmosphere, you see an increase in pressure. So you have that atmospheric at the top, 10 to the 5th, and all of a sudden as you go downwards to that closed tube, it's 10 to the 5th plus something else. So it might be 10 to the 10th or whatever, right? So as you go deeper in the atmosphere, as you go downwards, you see an increase in pressure. As you go upwards, you increase in altitude, right? You see a decrease in pressure. Really, I know looks like there's a lot written on this slide, but once again, this is kind of a reiteration. Whenever you have two different, two liquids that are the same, right? So here and here, you have the same liquid throughout, or the same fluid, right? Whenever they're at the same heights, they should have the same pressures. Now, if you were to have kind of an interface of two different fluids, so you have gas here, and let's say this is mercury or something, right? If you have an interface between two different fluids, then in order to figure out the pressure of that other, let's say this gas here, if we want to figure out what the gas pressure is, then the gas pressure, we can find it out here. But the way we can figure it out is knowing that the pressure here should equal the pressure there at the same height. Well, instead of looking or finding out, strictly what the gas pressure is alone, what we can do is figure out the pressure here at P2 using the fact that this height right here is in contact with the atmosphere. So if I start off here and I say I make this my PA, that's my atmospheric pressure, that's my area at the top there, right? And this is my PB at the bottom, right? What I can say then is that PA plus rho GHA equals PB plus rho GHB, right? At the bottom, what would my height be? 0, right? So this whole term goes to 0. So I'm left with PB, right? Or we can say P2 in this case if we're being consistent. P2 is equal to PA plus rho GHA, right? I know that the PA is that atmospheric pressure because it's in contact with the air. So it's simply 10 to the 5th pascals. And then if I have, let's say if this was mercury or whatever, it might be the density for 13,600 kilograms per meter cubed or whatever, right? So I just plug in the values there and I can figure out the pressure at 2. Once I have the pressure at 2, because I know that pressures at the same height, or 2 points at the same height will have the same pressure, then the pressure at 2 should equal the pressure at 1 here, right? The pressure at 1 is also equal to the pressure of the gas. At the interface, right, the pressure here, P1, should equal P2. And so I can simply figure out the pressure of the gas here just by figuring out, okay, well, at this interface, let me draw a horizontal line, figure out the equivalent height for it, look at the liquid or the other fluid that I have values for or that I can figure out, and then that way I can figure out here this pressure of the gas, right? So there's a couple different problems that we can go over with this as well, and it'll be reiterated a lot of times, but that's essentially how to figure out like different pressures when you have different fluids as well. Because there's no way for us, we don't have information, for example, about the gas density, we don't know anything about the pressure of the gas, obviously, so if we don't know any information about the gas, using the information that we have about this other liquid or this other fluid, we can say, okay, here's at the top, here's at the bottom, right? We can figure out what the pressure at 2 is, draw a horizontal line. Oh, at the same height, P1 should equal P2. And P1, because it's at the interface, right, between the gas and the other fluid, P1 should equal the pressure of the gas, right? So, yeah, that's pretty much it, honestly, for that stuff there. The only other thing that I would add is the gauge pressure equation here. So the gauge pressure is simply what a pressure reading would show you above or below atmospheric pressure. So the gauge pressure is simply equal to the absolute pressure of the gas, right, minus 1 atmosphere, or minus the atmospheric pressure, basically. So if I were to tell you, for example, let's say, okay, well, here, this is very simple, but what's the gauge pressure of atmospheric pressure? If I ask you, what's the gauge pressure of atmospheric pressure? 0, right? Because the absolute pressure of atmospheric pressure is 10 to the 5th pascals, right? If I subtract atmospheric pressure from atmospheric pressure, then 10 to the 5th pascals minus 10 to the 5th pascals should give me a 0 gauge pressure. And that tells me, obviously, like I said, when I say gauge pressure is a measurement of how much that pressure is above or below atmospheric. If you're at atmospheric, you're not above or below it, so it should be 0, right? Now, if I said it's 10 to the 6th pascals, let's say here it's 10 to the 6th pascals or something, right? At this height. If I ask what's the gauge pressure there, I take 10 to the 6th pascals minus 10 to the 5th pascals, and then that would be my gauge pressure, for example. Now, never just subtract 1 atmosphere. This is just telling you it's minus atmospheric pressure, right? Atmospheric pressure. So if your units of pressure are in torr, for example, if I said it's 800 torr, that's my absolute pressure at this height. If I'm at 800 torr, how would I figure out the gauge pressure? Subtract by 760, right? So I subtract by the atmospheric pressure in that respective unit. So atmospheric pressure is 10 to the 5th pascals. It's also 760 torr. It's also 760 millimeters of mercury. And it's 1 atmosphere. So if my pressure was in atmospheres, if I had 3 atmospheres as my pressure, I take 3 minus 1. If my absolute pressure was 780 millimeters of mercury, I take 780 minus 760. I've seen a lot of students that will do 780 just minus 1, right? You can't do that. You have to make sure that the units match up. If it's in pascals, subtract the atmospheric pressure in pascals. If it's in torr, subtract the atmospheric pressure in torr. And that's how you can get the gauge pressure. Yeah, this is kind of what I was talking about earlier, just an overview of that example. I know it's kind of messy, but I started off with this hydrostatic pressure equation. I made PB, that point here, a P2. And then obviously my height at B, the height at the bottom, is my reference height. So I started off at 0. So this term goes to 0 here. And then you're left with PA plus rho GHA, right? Which is, here's that pressure at the top, PA. And so from that, I can figure out the pressure at point 2 here, right? The pressure at point 2, I figured that out from this equation here. And then the pressure at point 2 is equal to the pressure at point 1. So I think I got like this big number in pascals. I don't know if they were asking for it in millimeters of mercury or whatever, but yeah, I think maybe they were asking for it in millimeters of mercury. So you can convert from pascals to atmospheres, and then from atmospheres to millimeters of mercury if you want, or you can say 10 to the 5th pascals, that's atmospheric pressure, and that's simply 760 millimeters of mercury, right? So if you go, that's how you can go from pascals to millimeters of mercury. And then if I want the gauge pressure of that gas, right, then I just take that absolute pressure minus the atmospheric. Like I said, atmospheric pressure is 760 millimeters of mercury, 760 torr, 1 atmosphere, 10 to the 5th pascals. So if I just subtract 760, I should get a gauge pressure of 310.08 millimeters of mercury, right? Like I said, if I want to figure out the pressure of the gas, I look at where the interface is at between gas and the other fluid. This is the point here. Realize though that the pressure at point 1 will be the pressure of the fluid at that height as well as the pressure of the gas at that same height. Like at this interface, the pressure of the gas and the pressure of the fluid should be the same, right? And then, yeah. So like I said, like if you have, start at pressure A, this is pressure B. If I figure out what P2 is, because they're at the same height, P2 should equal P1. And then at P1 here, that would be the pressure of your gas, right? It'd also be the pressure of the liquid at that same height anyway. And then obviously you can do your pressure calculations, get your absolute pressure minus your atmospheric, and then that would give you your gauge pressure, right? So this is barometers, how they work. I don't know if this is really necessary to kind of look at, but this is a very kind of niche example. For a barometer, you're going to have this tube basically that's going to be put up top of the liquid. You're going to have a vacuum pressure here at the top where you have zero pressure. I mean, once again, you're still applying the hydrostatic pressure equation in the end. I think this problem was asking you, like, what is the gauge pressure of the atmosphere? So this atmosphere right here, because it's in contact with the air, so that's the atmospheric pressure there. You would think that it's 10 to the 5th pascals, but in physics context and what we're doing when solving these problems, we're keeping the atmospheric pressure at a constant 10 to the 5th pascals. But as we know, anything in real life is never constant. So it'll vary. I can't remember what the range is. I think it's listed somewhere here in the slides, but obviously it won't be exactly 10 to the 5th pascals all the time. So what they're asking you is basically like, okay, what is it in real life? So they're giving you values like the height here is 70 meters, I think, for the tube here. And then they're asking you what's the actual, or like the real life atmospheric pressure. And then what is the gauge pressure as well. So I can say, for example, I'm starting off here at the top, PA, here's PB, right? So PA, the pressure there, because this is a vacuum, would be 0. And at PB, since I have my height here as my reference height starting from the bottom and I go to the top, then the height here is 0, and so this whole term goes to 0, right? So then I'm left with PB is simply equal to rho GHA, right? So I don't know why I threw in a negative sign here. That's unnecessary, but I think that was just a mistake on my part. But that would give you the pressure at B. There's your pressure at B. And then you can go from pascals to atmospheres by dividing by 10 to the 5th. So if we just take 95,200 pascals times 1 atmosphere is 10 to the 5th pascals. Pascals cancel out with pascals. And then you can see that you get 0.952 atmospheres. Obviously, the atmospheric pressure is 1 atmosphere, so you can see there's a little bit of variation in real life. If we wanted, once again, to convert it to gauge pressure, we would just take the absolute pressure that we figured out minus the atmospheric. So in this case, the absolute pressure is 0.952, so we subtract by 1 atmosphere to get the atmospheric, or the gauge pressure. And so we can see here that it's negative 0.05 atmospheres. All that really tells you, it's not telling you that there's negative pressure. It's just telling you that it's 0.05 atmospheres below the atmospheric pressure. So gauge pressure, think about if you're reading a gauge, right? It's just telling you how much you're above or below the atmospheric pressure. And these are all the pressure units that I was talking about. So 1 atmosphere, 760 millimeters of mercury. These are other pressures that aren't necessary. This, I don't really like this conversion factor all that much. I think you're better off doing or just going by the fact that atmospheric pressure is 760 millimeters of mercury, 760 torr, 1 atmosphere, and 10 to the 5th pascals. I think that'll allow you to convert between any units very easily and quickly and more accurately than maybe 1.3 kilopascals there. But let's see here what time I got. All right. So this is another situation with the hydrostatic pressure equation once again. This is just telling you which figure has the correct equilibrium position. They're telling you that water is poured into the tube, followed by oil. And the oil floats on the water because it's less dense, right? So if the oil is less dense, then obviously the density is less than water, right? So if I'm looking at these roughly, maybe without looking at my notes or something, which one do you guys think has the correct position? You can't? See. Yep. So honestly, I'll just move over here like that. I think that's better, right? So it is C, right? Because if we're looking at the differences in density as being what's causing these different images that you have here. So if we look at the hydrostatic pressure equation, PA plus rho GHA equals PB plus rho GHB, right? Well, we know that pressures at the same height should be equal to each other, right? So in theory, this pressure here should equal this pressure there, because they're both in contact with the atmosphere, right? So since they're in contact with the atmosphere, they should both be at 10 to the 5th pascals. But how do we get that same pressure with different liquids, right? Or different fluids? Well, if you look at B, for example, they have these same heights having the same pressure of 10 to the 5th pascals. But what they fail to account for is this difference in density. So if I were to say, I have this equation here, the hydrostatic pressure equation, PA is equal to PA plus rho GHA is equal to PB plus rho GHB. Then I see here that, okay, well, pressure at A has to equal pressure at B. They're both atmospheric pressure, but I have different heights. Or let's say, actually, let's eliminate B as an option. Let me show you why B isn't an option. So if the heights are the same, let's say HA is equal to HB, G is equal to G, PA is PB, because they're both atmospheric pressure, right? So if PA is equal to PB, HA is equal to HB, G is equal to G, then what does that mean for your densities? They should be the same, right? Because everything has to cancel out. But are your densities actually the same? No, because you have oil and you have water. You can't do that. So if we're looking at, for example, C and A, well, I circled that the other way around, C and A, right? Then we're looking at how those differences in density will account for those differences in height. So I know that here and here, you must have the same pressure because they're both in contact with the atmosphere, right? It must be same pressure of atmospheric pressure because they're in contact with the atmosphere. Same thing for here as well. So if I know that PA and PB have to be the same right off the bat, then my differences will come down to my density and my heights. So if I already know that let's call this the oil side, and this is water, right? If I already know that the density of oil is smaller than the density of water, then in order to compensate for that difference, because I know PA and PB will cancel out, so the only thing I have here is PGHA equal to PGHB here, right? So if the gravity is the same here, right? If the density of oil is smaller and the density of water is greater, then the height of the oil has to be greater than the height of the water. So you see how these arrows kind of cancel each other out? One's moving downwards, one's moving upwards. That's the idea here. So let's say, for example, if the density of water, I'm just using simple numbers. The density of water, or the density of oil, is 3, right? Let's say the density of oil is 3, right? And let's say the gravity is 10. Well, actually forget the gravity. If we're just looking at PHA, PHB, and P, I'm just saying, like, that's just easier than saying rho for some reason for me. I don't know, it's a habit. But let's say here you have the density times the height there for water, right? Then if, let's say, density is 3 for oil, and the density for water is 4, right? And let's say this term, we want it to be equal to 12. If we want this term here, density times height, to be equal to 12, then 3 times 4 is 12, right? We'll look at here, 4. If I want this also to be 12, because they have to be equal, then 4 times 3 is 12 as well. What do you notice about the heights? Smaller, right? So the height of water would have to be smaller, right, to make up or compensate for the fact that the oil density is less. So if the oil density is 3 versus 4, right, if the oil density is smaller, then the density of the oil has to be, or the height of the oil has to be larger than the height of the water in order for both sides of the equation to be the same. Does that make sense? Cool? So that's why C would be the best here. That would be the best option there. This is another example, kind of continuation of that. Let me kind of skip toward this section of it here. It says, consider the setup shown below, where oil is poured onto water in a tube open on both sides. Water has a density of 1 gram per milliliter, and oil has a specific gravity of 0.8, right? So specific gravity, remember we said that was the ratio of the density of the substance, so in this case oil, to the density of water. So if I have this specific gravity of 0.8, then I know 0.8 equals density of the substance, which is the oil, divided by density of water. I know that the density of water is 1,000 kilograms per meter cubed. So if I just multiply over 1,000, I can get the density of oil. And the density of oil in that case will just be 800 kilograms per meter cubed, right? Make sense? So that's my density of oil there. Now, if they're asking, I think they're asking first, what is the gauge pressure? I don't know why they asked for the height difference first, but let's see here. Yeah, okay. So if I want to figure out the height, let's start with the height difference first, okay? So if they want the height difference between H2 and H1, H2 minus H1, right? Then I can use the hydrostatic pressure equation to even figure out what I think, what was it, H1? No, H2, my bad. So they gave us H1, that's 10 centimeters. I want to figure out what H2 is. Right, I want to figure out what H2 is. So the way I can figure out H2 is by using the hydrostatic pressure equation, because I know that if I have PA plus rho GHA is equal to PB plus rho GHB, if I start from the bottom here, here's my PB, here's my PA, well, I know that my atmospheric pressure should be 10 to the 5th pascals, right? I think what I did here is that I factored in gauge pressure. So if I'm using gauge pressure for atmospheric pressure, right? The gauge pressure of atmospheric pressure, like we said, is 0. So this PA would go to 0 if we're using gauge pressures for our pressure values, which is something you can do. And so then PB would be your gauge pressure at the bottom here, right? And so the bottom height, once again, the height will cancel out because it's 0. That's our reference height. And so we're left with PB is equal to rho GHA. So we have that 800 kilograms per meter cubed as our density, multiplied by the gravity, multiplied by the height that we're looking for. I think, let's see here. Did they ever give us the pressure for this? I think we had to figure it out. Yeah. I don't know why the slides are like reversed. I think you had to figure out the gauge pressure here first, and then you can figure out the height difference. So I don't know why these slides are reversed, but okay. So first you figure out the gauge pressure at the bottom here, and then you figure out the height differences. So the reason why is that I know the pressure here is atmospheric, right? That's 10 to the 5th pascals. I don't know what the pressure here is. The relationship between these two pressures factors in height due to the hydrostatic pressure equation. So I know the pressure at the top is equal to density times the gravity times the height is equal to the pressure at the bottom plus density times gravity times the height. So if I know the pressure at the top, right, and I want to figure out the pressure at the bottom, I can use this equation, figure out what the pressure at the bottom is. So I know the pressure at the top is 10 to the 5th pascals, density is 1,000, and then times 10 times 0.10, that's the height here that will give you H1, right? That's my H1. So what I can do is then, once I have this pressure at the bottom, PB, this pressure at the bottom here, that's 101,000 pascals here, right? So that's my pressure at the bottom using this column of fluid here. Once I have this pressure at the bottom, I know that the pressures here that are at the same height should be equal, right? So that pressure at the bottom here should be equal to the pressure at the bottom there, because they're at the same height. So once I have this pressure at the bottom for this other fluid here, then I can go back and use the hydrostatic pressure equation again, use those heights. Now I have this height here that I'm looking for. So I have pressure at A plus rho GHA is equal to pressure at B plus rho GHB. So here they wanted us to use gauge pressure in the problem. So the gauge pressure at the top is 0 because it's atmospheric pressure. And then the pressure at B, we had figured that out from the previous part here, which is just taking that absolute pressure minus your atmospheric, right? Minus that 10 to the 5th to get 1,000 pascals as your gauge pressure, right? So this is the gauge pressure at the bottom here that we figured out from the fact that this pressure here should be the same pressure here because they're at the same height, right? So once we have that pressure at the bottom, we can then set it equal to the density times the gravity times the height of that other fluid, right, which was the oil. So that way we can figure out that unknown height that we're looking for. So that gives us a height of 0.125 meters, which is that H2 And then we can subtract H2 from H1, and H1 was 10 centimeters. So you just take 0.125 minus 0.1, and that's equal to 0.25. I know that one was kind of confusing because I jumped from slide to slide, but does that make sense? Sort of? A little bit? Yes, no? Feel free to, like, I will repeat this if need be, like, I don't mind. What's that? Yeah, so let me repeat it properly this time because I know I like messed up because the slides were reversed. But once again, they're telling us that they're pouring oil on top of this water column here, right? Telling us that the water has a density of a gram per milliliter, which that's the standard density of water, right? And we know from before that the density of water is 1,000 kilograms per meter cubed anyway, right? So they're asking us two things in this problem. They're asking us what's the gauge pressure at the oil-water interface here, what's the gauge pressure there. They're also asking us what's the height difference between H2 and H1, right? So let's first start off this time with figuring out the gauge pressure at the oil-water interface. Now, if we go down here, right, we're looking at the gauge pressure at the bottom here. Our issue is that we don't know the height yet. We don't have access to the information about the height 2. We do know the height 1. Well, how can we figure out the pressure here if we don't know the height of this column here? If we don't know H2, how can we figure out the pressure here? Exactly, it's equal to the pressure that would be at the same height. If we just simply draw a horizontal line, we're like, okay, well here, this pressure here at the bottom of this water, not of the oil, of this water, should be the same because they're at the same height. So this PB here will be equal to the PB there. So I do have this height though. They gave that to me as 10 centimeters or 0.1 meters. So using the hydrostatic pressure equation, I can say, okay, well PA, where A is at the top of this water column, and this is PB, I can say that PA, which is my atmospheric pressure because it's in contact with the air, plus rho GHA is equal to PB at that bottom, the water column, plus rho GHB, right? So at the top, it's 10 to the 5th pascals because it's atmospheric pressure, plus the density of water times the gravity times the height of that water column. And then we know that the height at the bottom is our reference height, so it goes to 0 here, and we're left with PB at the right. Do you have a question? Wait, say that again?
On the left-hand side, not with the oil, we know that it's the same pressure at the top of the liquid and at the right there where you're
Yeah.
putting it, because it's the same.
Yeah, even though that they're different fluids, they should have the same pressure because they're at the same height, right? That's not? Okay. They have to be the same? Oh wait, sure, yeah. So they do have to be the same fluid, my bad. So I think, yeah, you do have to factor in the differences in density values, my bad. Yeah. Because at the oil-water interface, whatever, so we have this pressure here that we're going to figure out. We draw a horizontal line. The pressure here is not only equal to the pressure of the fluid that's like right before the oil, but it's also equal to the pressure of the oil right after the water. Does that make sense? So because you have this intersection right here, it's like split evenly between water and oil. So whatever the pressure here is, it's equal to the pressure of the water that's just before the oil, and it also happens to be the pressure of that oil just after the water, because they're just so close there at the interface. But once we have this set up, like I said, this height here goes to 0 because we're starting from the bottom. And so we can just figure out then from the hydrostatic pressure equation what the pressure at the bottom would be. And then they asked us what the gauge pressure is. So once again, for gauge pressure, you just take the absolute pressure minus the atmospheric pressure. And since in pascals, you just subtract 10 to the 5th. And that gives us a gauge pressure of 1,000 pascals, right? 1,000 pascals at the bottom here. That's our gauge pressure. Like we said, since they're at the same height, 1,000 pascals is now the pressure at PB for this oil column here as well, right? So if we go back now, and they're asking what's the height difference, H2 minus H1, well now I can figure out what the height is, because I know the pressure at the bottom, and I know the pressure at the top. So now I can relate their heights. So if I'm using gauge pressure once again, because I have the values of gauge pressure anyway, it's just easier, The pressure at the top, atmospheric, should have a 0 gauge pressure, because 10 to the 5th minus 10 to the 5th is 0. And then pressure at the bottom, the gauge pressure for that bottom part right here, is 1,000 pascals that we figured out from the previous part. Once again, we're using the reference height as the bottom, so the height would be 0. So this whole term goes to 0. So then we're just left with PB is equal to rho GHA, where the density now is not the density of water, it's the density of the oil that we're using, right? So 800 times the gravity times that unknown height is equal to that gauge pressure at the bottom there. And so then we can just solve for the height. And then if they're asking for the height difference, H2 minus H1, well, this H2 is 0.125 meters. And we can subtract it from H1, which they gave as 10 centimeters or 0.1 meters. So just subtract 0.125 minus 0.1, and then that gives you 0.25. Does that make sense the second time around? Okay. Yeah, go ahead. Yeah, my bad. 0.025, yeah. There goes my math abilities right there. But yeah, thanks for pointing that out. But yeah, does everyone understand like that general concept of how to relate the columns together and stuff? Do you have a question?
I can answer that.
Okay.
You have to do the gauge pressure, and this one's for because we're in a variable inside.
Yeah. Yeah, I don't know why they had the height difference first. I don't know if I just like rearranged the slides on accident or what, but yeah. That's it for that stuff up there. This is what I was talking about earlier with how we can understand why, as we increase like in depth or we go downwards in the atmosphere, we see an increase in pressure. So the air's density and pressure are greatest at the Earth's surface, and then the density and pressure, or let's say, forget the pressure for a sec, just the density of air decreases as you go upwards, right? As you go up in space, density of air decreases. And so if we're looking at what pressure is, remember we said pressure is force divided by area. So that force, let's say that's the force of gravity, right? So that's the weight of the air. So force of gravity, the weight of the air, mg. Remember we can write mg as density times volume times gravity, right? If the density of the air decreases as we go upwards, right, as we go up into space, the density of the air decreases. We know that since this is mg is equal to rho vg over a, right? If the density decreases, what does that mean for our pressure? What? I said if this is our force of gravity here, and we can rewrite it as density times volume times gravity. If we were to decrease the density of the air, right, as we go up into space, the density of air decreases, what happens to our pressure? It decreases, right? So that's kind of the real life connection there as to how or why we see a decrease in pressure as we go upwards and an increase in pressure as we go downwards. This is, I don't know, is this necessary to kind of go over? I mean, like, for a doctor, yes, but like, yeah, I don't think this is going to be like necessarily on the exam. Only thing is like, for a real life situation, if you're measuring blood pressure, you measure it at the height of the heart, because otherwise if you measure upwards like this or downwards like that, you're not going to get the exact reading because you're not at the same height as your heart. Right? Like, but that's about it that you need to know for those two slides. Screw buoyancy. Screw buoyancy, I'm not doing that shit right now. But yeah, I think Pascal's principle is really important. So Pascal's principle is just telling you that any change in pressure applied to any surface of an enclosed, incompressible fluid causes an equal change in pressure at every point in fluid. So that just means if I apply a change in pressure here, I should see the same change in pressure at every single point in the fluid, right? Now, also with Pascal's principle, right, if I have pressure as force divided by area, right? Well, if the pressure here has to be the same as the pressure there, what if I apply a really large force, really large force over a smaller area? Actually, no, other way around. Small force over a small area. If I have a small force over a small area, if I look at this larger area here, I'd have to have a really large force to exert the exact same pressure. So let's say, like, I don't know, yeah, let's say your pressure is 10, I'm not going to assign units. If your pressure is 10, right, your force is, let's say your force is 20 and your area is 10, or my bad, 2, right, that's your smaller area. If I want that exact same pressure value, because remember this is pressure is equal to force over area. This is of the left piston right here. For the right piston, if my pressure is that same 10, but now I have a much larger area, let's say, let's say 10 here, right? Then in order to get the same pressure, my force has to be 100 now instead of 20. 100 divided by 10, 10, 20 divided by 2, 10. Same pressure, right? According to Pascal's principle, the same pressure would be applied for all points in the fluid, right? But then that would mean if I have a difference in area, right? If that piston was different, then the force would have to change, for example, to compensate and make sure you have the same pressure. Does that make sense? Someone have a question over here? I saw something. Do you guys have a question? Sure? Okay. And this is just an example of it. I don't think this is necessary to kind of go over because it's just, once again, a manipulation very similar to what I did, except that obviously the area when you're doing it of a piston, it's going to be pi r squared because it's a circle, right? So, it's just asking, like, you have a specific pressure, you have a specific area, what's the force? And then you know that, I guess you must have the same pressure here as there, and so it's just asking you to manipulate and figure the difference in forces based on the difference in areas. So that's not too bad either. This one I got a couple questions about, but the reason is, I think, is this based on different professors and how they interpreted this and whether or not they wrote if height matters or not. For Pascal's principle, we know that any change in pressure applied should be the same pressure applied throughout the fluid, right? So in that case, if they're asking you, if you have this cylinder with a movable piston with a uniform fluid, if the corks are all in equally tightly, which one is most likely to pop off, right? So if I'm applying the same pressure throughout, pressure should equal force over area, right? So if it's the same pressure here, same pressure there, same pressure here, same pressure there, should all the forces be the same? Yeah, right? Because pressure is equal to force over area. If the pressure is constant throughout because of Pascal's principle, I should see the same force throughout. And so if they're all pushing against the corks with the same force, they should all pop out at the same time if we're going by that. However, I think in the newer slides for Dr. De Jong, the thing is, I think they said height isn't negligible here. So the difference in height matters. Since there is a difference in height between 1, 2, 3, and 4, right? This cork number 4 here is at the greatest depth or height, right? So remember what we said about pressure. As you increase your depth, as you go downwards in the atmosphere, you see an increase in pressure, right? So in theory, if the heights weren't negligible, if we cared about the heights, then cork 4 would pop off the first one because the pressure here would be the greatest. Pressure is the greatest means the greatest force, right? If the heights were negligible, so we don't care about the heights, then all of them will pop off at the same time because the pressure would be the same there everywhere. Does that make sense? Just to clear up that idea there. But yeah, in this case, for our year, they told us that heights weren't negligible, so the heights did matter. And so in that case, cork 4 would pop off first because it's at that greatest depth. This stuff is the week 13, so I'll skip that for now. Flow rate is just measurement of volume per second, right? And then this is the equation for the flow rate here, and that's equal to the area times the velocity that the fluid is moving at, and that gives you the flow rate. Let's see here. This is a simple example of how to figure out flow rate. So if you have a garden hose with an inside radius of 1 centimeter, hose can fill a 10-liter bucket in 20 seconds. So there's our time, right, at 20 seconds. And they told us, here's the, what do I want to say? The volume there, right? So if we just divide the volume divided by the time, because remember, flow rate is volume divided by time, we can get a flow rate there of 5 times 10 to the negative 4th. And then if they're asking what the speed is of the water, we know that the flow is equal to the area times the speed. They gave us the radius of 1 centimeter. We're assuming that hose obviously is kind of circular or rounded, right? And it has a cross section of a circle. So in that case, we can just do pi r squared, where r is 1 centimeter. And so we just have this pi r squared. 1 centimeter is 0.01 meters, right? So we just divide the flow rate divided by the area. We can get the speed, which is 1.6 meters per second.
Hey guys, just make sure you have to follow UIC's policies and just make sure you guys are wearing your masks. If you don't have one, there are actually not here as well.
Yep.
Yeah, thank you.
Does that make sense so far? But yeah, now we get into continuity equation. So for continuity, right, it just tells you that the flow is equal throughout the fluid, right? So if you have a moving fluid, the flow rate should be the same. And then flow rate should be the same as well with like differences in area too. So if you have a difference in area, then you should see a difference in velocity or speed as well. What's that? No. Thank you. I don't know. Anyway, yeah, so your flow rate should be the same even with differences in areas, because there's going to be a compensation with the velocity. So the fluid might be faster or slower depending on the change in area, just to have the same flow rate. But the key is that the flow rate should be the same throughout the fluid, right? That's your continuity equation. Skip over this part, I think, as well, because this will just be the same. So if they're asking you, blood flows through the coronary artery, that's partially blocked here. Through which part of the artery is the flow largest? Well, the flow would be the same throughout, once again. Flow rate is the same, but in order for that flow rate to be the same, if we have a change in area, because obviously this part is narrower, right? If we have that change in area, we should see a change in the velocity or the speed to ensure that the flow rate is the same, right? So if we say Q1 here is equal to Q2 there, right? Then A1 V1 is equal to A2 V2, right? So if we were to decrease the area, we should see an increase in speed. Decrease in area, increase in speed. Increase in area, decrease in speed, right? Now, if I just do some very simple mathematical kind of examples here, if I have A1 V1 equals A2 V2, if I said the area of the first one was 4, right? And the area of the second one, because it's narrower now, is 3. If I want to make this product 12, then I know that the speed here has to be 3 for that first section that's not blocked. But that means then, if I want to maintain that flow rate of 12, then here on the right, I must have a speed of 4. So you can see that the speed increased from 3 to 4 when the area decreased. So when area decreases, speed increases, right? If the area increases, then the speed decreases. So when you have a narrower artery, a narrower passageway, right, the water or the blood or the fluid is going to want to move faster, right, in order to move that exact same amount of blood or the exact same amount of water, that same volume, right, per second. So it has to speed up because it's blocked now. As opposed to if you have a lot of room, it can slow down, it can relax because it's moving at a relaxed pace, right? So the flow is the same, but the speed isn't. And so if they're asking you what is through which part of the artery is the speed of the blood the largest, it should be the largest in that narrower area, because we said if the area decreased, then the speed should increase, and if the area increased, speed should decrease. Make sense? This is another example as well with A1 V1 equals A2 V2. But let's see here. So they said a garden hose has an inside diameter of 16 millimeters. Hose can fill a 10-liter bucket in 20 seconds. So 10-liter bucket, 20 seconds, that's our flow rate right there. 10 liters, we had already converted that earlier, and that was 0.01 meters cubed divided by 20 seconds. That gives us our flow rate. And then from that, because also we have our area that we can figure out, because we have our diameter is 16 millimeters, so our radius is 8 millimeters, right? So using that information, we can figure out what the speed is at that first area there. Now they said, what diameter nozzle would cause the water to exit with a speed 4 times greater? Well, if this is the speed, if I want a speed that's 4 times greater, 2.5 times 4 is 10 meters per second, right? So then, once again, if the flow rate is constant throughout, my Q is going to be the same as before. My Q is the same as before. But now my speed, instead of being 2.5, it's 10. So then what would my new area be, or what would my new radius be? So I plug in that pi r squared, and then I can solve for that. And then the diameter would be 8 millimeters, so your radius would be 4. Does that make sense? Okay, these are just kind of all repetitive kind of equations, or the problems, just to kind of explain once again that flow should be the same, but the changes that you see are in area or in speed, right? If I decrease the area, I increase the speed. If I increase the area, I decrease the speed. I'll skip over this too as well a little bit. But this is what you see here as well. So if I decrease that area, I see an increase in speed. If I increase the area, I see a decrease in speed. But yeah. Here we have Bernoulli's equation, which is just an extension of the hydrostatic pressure equation, but it also factors in movement of a fluid, right? So here it tells us that at a higher, pressure is higher at a point where the fluid is moving slower, and the pressure is lower where it's moving faster. And I'll explain why here in a sec, because it sort of doesn't make sense if you use your intuition, but there's an explanation here using the equation. So what they're saying is pressure is higher when the fluid is moving slower, and pressure is lower when the fluid is moving faster. So you would think that, okay, well, if I'm putting more pressure, if I'm squeezing this thing, it moves faster, right? That might be one way of thinking it, right? If I squeeze on something, I'm exerting pressure on it, I'm putting stress on it, I'm squeezing it, then if that squeezed portion goes faster, then okay, the higher pressure means faster fluid. That's your intuition, right? That's how you think about it. But it's actually the opposite, and I'll explain why here in a sec. So that comes from the fact that of this relationship here with Bernoulli's equation. So the way I like to explain it, and the way I kind of discovered how to explain it was by studying for the MCAT, and the way they kind of explained things was in terms of static pressure and dynamic pressure. So in Bernoulli's equation, you have this part of the hydrostatic pressure equation, which is your PA plus rho GHA is equal to PB plus rho GHB. What they add is the pressure due to the movement of fluid. So the movement of fluid alone, just by having movement of fluid, that causes pressure. And that's 1/2 times density times the velocity of that fluid at that specific point squared. So the way they explained it in the MCAT studying that I've done is that there's a concept called static pressure and there's a concept called dynamic pressure. So static pressure, think about static, not moving, stationary, right? So that's the pressure due to just simply differences in height with just the fluid just there, right? Dynamic pressure is, once again, that kind of as the name implies, dynamic as in movement, right? That's the pressure due to the movement of the fluid itself. And that's why we see it factors in the velocity of the fluid, right? So the idea here is that since there's an equation, or there's an equal sign in the middle here, right? So both sides have to be equal to each other. If I see an increase in one type of pressure or another, I might see a decrease in the other type of pressure just to compensate things, right? So essentially, if I were to see here, I know that as I decrease area based on the continuity equation, if I'm maintaining flow, if I decrease my area, I should see an increase in my speed, right? That's a fact for sure. But if I increase that speed, right? Let's say here, this is the speed here for my dynamic pressure. Let's say that speed is 3 meters per second or whatever. If I were to increase that speed because of that decreased area, that means that my dynamic pressure for that second point, my dynamic pressure here, is greater than my dynamic pressure in this more relaxed portion, right? So if we just look at these as two big terms, A and B, if my dynamic pressure here in that squeezed portion is bigger than the dynamic pressure here in that relaxed portion, so if this is bigger than this, right, then this term right here should be smaller than this term. So if I have a larger dynamic pressure due to a faster moving fluid, I should see a lower static pressure. And if you look at what static pressure has, it has a value of that absolute pressure there. So when you have a decreased area, due to the continuity equation, you see an increase in your speed. At the same time, with that concept of dynamic pressure that I explained, if we look at these as two big terms, right? Static pressure and dynamic pressure, right? If the dynamic pressure, which is the pressure due to the movement of fluid, is greater because the fluid is moving faster, if this velocity is greater than this velocity, then I see a greater dynamic pressure. If there's more dynamic pressure than this dynamic pressure, there should be less static pressure than this static pressure. So, in a more constricted area, this area is smaller, I should see greater speed and I should see lower pressure. In this larger area, I should see slower speed and a greater pressure. Once again, don't use your intuition in this case because you're thinking, oh, if I squeeze it, I'm putting more pressure on it, right? And that should cause a faster speed. No. Got to think about it first with the continuity equation. If I'm maintaining flow, there's a decrease in area, I should see an increase in speed, right? If I see that increase in speed, it increases my dynamic pressure. If my dynamic pressure increases on that constricted area, my static pressure has to go down to maintain a value that's the same on both sides, right? Once again, if I do mathematical manipulation, very basic, right? If I say this whole term here is 3, right? And I want to make my static pressure, let's say that's 9. 9 plus 3 is 12. In order for me to have 12 on both sides, let's see what happens. So this is 9 and this is 3. So the dynamic pressure is 3 and the static pressure is 9. If I have that decrease in area, I see that increase in speed. That's a fact. That's by the continuity equation. So if I go from 3 to 4 for my dynamic pressure, I increased in speed, right? I increased my dynamic pressure. In order to maintain 12 on both sides, instead of having 9 plus 3, I should have 8 plus 4. So what do you see happen to the static pressure? You went from 9 to 8. You decreased your static pressure, right? So that means in that smaller area, once again, smaller area, greater speed, lower pressure. Larger area, smaller speed, greater pressure. Make sense? Feel free to take a screenshot of that if you want, because I know it's a very important concept. And I'm pretty sure, correct me if I'm wrong, because you've gotten way far with this MCAT study that I have. This is the Venturi effect, right? Yeah. So, yeah. Does that make sense so far? Cool. The second part, just the, I uploaded on YouTube. That's the one session that I had that didn't have the audio proper, the quiz review. That was messed up. But yeah. Everyone good for this stuff so far? But yeah. Does that make sense more with the static pressure and dynamic pressure thing? Does that kind of help you understand it a little bit more? Because I felt that was the best way that I could understand this. Like I understood this more from studying the MCAT than I actually understood when I took the class. So yeah, hopefully that helped a little bit. I know it's kind of extra, but it helps to understand this example problem here, which is if you have gas flowing from left to right through the pipe, at which point does the pipe have the smallest inner diameter? If I have a small diameter, what does that increase? What does that mean for my area? If I have a small diameter, what does that mean for the area? Smaller area, right? So it's essentially asking you, forget the diameter, it's essentially asking you which point has the smallest area, right? Well, how do I kind of figure that out, right? All I see here is that there's 3 points, and then there's liquid being pushed essentially downwards, right? So this, by the way, this is the liquid, and this is the gas, and they told you that gas is flowing. So if I just look at these different liquid versus gas heights that you see here, I don't know exactly how to ask this, but which point do you think the gas is pushing most on the liquid? Wait, did someone say it over here? I didn't hear. C, right? So the gas is pressing the most on the liquid here. Keyword pressing. Pressing, pressure, pressure, pressing, right? So if that gas is pushing or pressing the most on the liquid there, what does that mean for the pressure at that point C compared to the other ones? It's the greatest pressure, right? It's the greatest pressure at point C. Pressure is greatest at point C. That means force is greatest as well, because pressure is equal to force over area, right? So they're exerting the greatest force, they're exerting the greatest pressure, because they're pressing the most on the liquid. Now, remember what we said about the Venturi effect, what we said about Bernoulli's equation, what we said about static and dynamic pressure. Well, they're asking you which point does it have the smallest diameter or the smallest area, as we said. If you have a small area, what does that mean for your velocity? Your velocity increases, your velocity is greatest, right? So it's essentially asking which point has the greatest velocity, right? Which point has the fluid or the gas moving the fastest, right? So I know that the pressure here is the greatest. This is the greatest pressure. Once again, if I go back here, remember what I said about a small area, it has a greater velocity or a greater speed. What about the pressure? Lower pressure, right? If I have a relaxed area, greater area, I have a smaller speed, and what happens to my pressure? Increase in pressure, right? So you see that increase in pressure there. Would C have the fastest gas or not? You say, what are you saying? No. Right, because if it has the greatest pressure, it actually has the slowest speed. If we're going back about that idea of static and dynamic pressure. Because if you have that, if you have the greatest, if you have the greatest greatest static pressure there at point C, because it's pushing down the most static pressure would mean the least dynamic pressure. Because remember, both sides have to be equal to each other. If this term is the biggest, or if it's bigger than this term over here, right, then if this term is larger, this term has to be smaller than this term, right? So essentially what you see here, this pressure B at point B here is pressing down the least. You see, it's barely moving the liquid. So it has the lowest pressure. The lowest pressure, the lowest static pressure would mean the highest dynamic pressure, right? Let's say if we wanted this side, once again, if I'm just going with mathematical manipulation, if I wanted this side to be equal to 12, once again, I don't know why I have an obsession with 12 today, but if I started off with, let's say, a static pressure of 6 and a dynamic pressure of 6, right, for point A, for example, right, then at point B, if we're looking at point B where it exerts the least amount of static pressure, it's pressing the least on the gas, that static pressure might drop down to like 2. Well, in that case, my dynamic pressure has to shoot up to 10, right, to maintain that value of 12. So in that case, you can see the area or the point with the smallest pressure, smallest static pressure, should have the greatest dynamic pressure and therefore the greatest velocity with the smallest area, with the smallest diameter. So that's point B. Make sense? Yeah, this is really needed. This stuff, we never went over lift. These last couple, this example problem, I went over it in depth with the quiz review, so I don't think it's like super necessary to do it, because I want to get to some practice problems. Same thing for these last couple ones. I hate to kind of like skip over them, but we're going to do some of the exact same ones here in a sec. So I think that's about it for the lecture kind of overview for the week 12 stuff. So yeah, do you guys have any questions? Let me actually end the recording here a sec, but that's it for this stuff for now.